Being students of physics, we are accustomed to hear in almost every classes from our teachers something like, well, you have studied it in your previous classes, so I will not go to teach those terms again. I can assume you know that. And we say, well, it's okay, we have studied it, we know it. But now the question is, do we really have that concept? Let's check. Today, in this video, I will try to describe some of the basic terms of physics in my words. Well, again, welcome to Skyline. A particle is ideally defined to be a point-like entity that can have mass, can have charge, but neither any volume nor any spatial extension. That is, it cannot have any length or any other dimension. But it is obviously the ideal case. We can assume large bodies, even the Earth, to be a particle, but in special cases. When we talk about the Earth moving around the Sun, we can assume Earth to be a particle, because here the motion of Earth, in this case, it is irrelevant. The shape of Earth or the size of Earth, it is irrelevant when we talk about the motion of Earth. But even when we talk about a disk, a rotating disk, we can measure its moment of inertia, which obviously takes the concept of spatial extension. We know a particle with mass can attract another particle with mass. A particle with charge can attract or repel another particle with charge. Thus, we find the existential status of a particle. But what about space and time? The fact is, classically, space and time has no existential status. The concept of space comes into action when we talk about an object with extension or two particles having separation. In this universe, there are millions of planets, stars, and also in this world there are millions of objects that have separation. So this gives rise to the concept of space. Till now, I am talking about the static organization of matter and space, but when it moves, we tacitly assume that space stays as it was, only the particle or that matter moves. I repeat, we assume that space stays as it was. This is an assumption. Now, at this point, when the movement occurs, we seek for another parameter and we call it time. Time is that parameter that characterizes the changes or movement of that organization of matter and space. But again, that problem arises. Time, like space, has no existential status. We cannot find any phenomena like attraction, repulsion, or something like generation of waves, so that we can prove the existence of time like space. So, classically, they are just mere concepts. That's why it is difficult to properly define time and space classically. Till now, classically we assumed that space and time are two parameters, they are independent and they have no existential status. but I used the term classically again and again. Why? Because it was Albert Einstein who stated that time and space are not independent parameters. They depend on each other. So we better talk about another parameter, and that is space-time. And also, when he formulated the general theory of relativity, he combined all these and stated that space-time can have existential status too. When space-time fluctuates, it gives rise to the gravitational waves that we can observe, that we can measure. That's how space-time can have existential status too. So the concept of space-time is now combined, and together we get the new concept of space. Someone has broken the name of Einstein, and it's symmetrical. It gives three parts. The first one, E, that means one in the German language. The second one is ST, that stands for space-time, and the third one is again EIN, and that's one again in the German language. So we get space-time is one thing.